Okay, this is exam 5 for physics 102. Here you're just supposed to select the correct ray diagram. This is a convex mirror. Let's just go through each one. For A, right here we have, let's see, the first ray goes parallel to the axis and then it goes out. It's diverging, but such that it goes back to the focal point. So that one checks out okay. This one goes up such that if you were to trace it forward, it will go through the focal point, and then it goes parallel to the axis. Oh, so there we go. So that's the right one. We trace both of those back and find the upright, smaller virtual image. So A is the right answer. These are wrong for various reasons, but I'll leave you to go in those over your own. See, here we have a convex lens for A right here. I have a light ray that comes up as if it's originating out of the focal point, and then it goes parallel to the axis. That's correct so far. Here, this goes parallel to the axis, and then through the focal point. That one's correct. This one is not correct, and actually the image would be formed back here. All right, this would be a virtual upright bigger image. Looks like what we have right here. So here I have rule number 1, through the focal point parallel to the axis. Remember, it's originating from the focal point back there, so this one checks out okay. This one's parallel to the axis and through the focal point. That one's okay. And this one's straight through the center of the lens. And then I can trace those 3 divergent rays back to find where the image is. This is like a magnifying glass. A negative magnification indicates that the image is which of these? A negative magnification means that it is inverted. So A is the right answer. A convex lens produces an image twice the size of the object. The object is placed where? Well, if it produced an image that's twice the size of the object, that's going to be an object that is in front of the focal point. This is like a magnifying glass. So well, the only one that is between the focal point and the lens is half a focal length in front of the lens. Concave mirror makes a 3 centimeter image of a 6 centimeter object when the object is placed 10 centimeters from the mirror. What is the focal length of the mirror? Okay, well, it's a concave mirror, and it's making a smaller image. Because it's making a smaller image, I know that this is upright. So this concave mirror is making an upright image. So not an upright image, an inverted image. So my magnification is going to be negative HI over HO, which is going to be 3 over 6, or negative 1/2. I know that it's inverted because if my image was going to be upright, remember this is like a shaving mirror. If my image is upright, that means that I'm holding my object inside the focal point and it looks big, like in a makeup mirror. And if it looks big, like in a makeup mirror, you appear upright. Right? That's for a concave mirror. But here, the image appears smaller, so therefore I know that it has to be inverted, because that means that the image is going to be behind the focal point. Okay, that we could stop there because I know that the object is at 10 centimeters. So then I know that it can't be at the focal point. It has to be A. Well, let's go ahead and work through this. So if my magnification is equal to negative 1/2, I want to know the focal length of the mirror. I know that P is equal to 10 centimeters. This is equal to negative Q over P. So negative 1/2 is equal to negative Q over 10 centimeters. So Q is equal to 5 centimeters. And then I can find the focal length. The focal length is 1 over Q plus 1 over P. So the negative 1, that's 1 over 5 plus 1 over 10. Negative 1, that's going to be 10 divided by 3, which is 3.3 centimeters. All right, so the right answer here is going to be A. Number 6, optometrists describe the power of a lens as the inverse of the focal length, where the focal length is in meters and the power is in diopters. So when you hear about glasses, they're described by diopters, and it's a measure of the strength of the lens. How much does it bend the light? So the magnification of a 3 centimeter high object placed 5 centimeters from a certain lens is -1. What is the power of the lens? So I need to find F. I know P is equal to 5. I know that the magnification is -1. That's negative Q divided by 5. So I know also then that Q is equal to 5. So I can find F. That's 1 over 5 plus 1 over 5. That's going to be 1/5, 2/5, 2.5 centimeters. All right, so my power then is going to be 1 over, not 2.5, but 0.025 meters. I have to convert it to meters. And that's going to give me a power of 40 diopters. So C is the right answer. Which of the following can make a real inverted image? Okay, let's see. Not a plane mirror, not a concave lens. A concave lens can only make a virtual upright image. And likewise, a convex mirror, like a security mirror, can only make a virtual upright image. So A is the right answer. Okay, here's a 2-lens system. I have L equal 32, F1 equals 6, F2 equals 8. And this distance, P1, I'll call it, is equal to 24 centimeters. And I want to know the magnification. So first, I take the first system. I want to find Q1. That's 1 over 6 minus 1 over 24. That's 4 over 24 minus 1 over 24, which is 3 over 24. 1/8 inverse is 8 centimeters. Okay, and then my magnification due to that first lens is -1/3. Now, that means that my image is going to be 8 centimeters. It's going to be right about here. It's inverted, and it's 1/3 the size of the original object. That means that P2 is this distance, 32 minus 8, or 24 centimeters. And so I can do the whole thing all over again. So Q2 is going to be 1 over F2, which is 1 over 8, minus 1 over 24. 3 over 24 minus 1 over 24, that's 2 over 24. The inverse of 1/12 is 12 centimeters. And then I can find my M2. P2 is 24. All right, and then to find my total magnification, I take the product of these two numbers, which will give me 1/6 is the right answer. Spherical mirror can have which of these? A spherical mirror does not have chromatic aberrations because it doesn't refract light. It has spherical aberrations. Real images are usually formed behind a concave mirror. No, if you have a real image, it's going to be the object is here, the image is here. It's in front of a concave mirror. In front of a convex lens, all right, if you have a real image for a convex lens, if you have a real image for a convex lens, it's going to be opposite the side of the object, so it's not in front. You do get a real image on the human retina, right? Because you have a convex lens looking at an object that's outside the focal point of the lens. So you get a system that looks like this. You have your focal points here and here. This is your object, and your image is formed over here, like on the human retina. And by the way, if you try to focus on something inside the focal point, it doesn't work. Not behind a concave lens, so C is the right answer. All right, a mirror produces an upright image of an object. The object is 4 centimeters high, and the image is 2 centimeters high. So I know that my magnification, first of all, it's upright, so it's going to be positive. My object is 4, my image is 2, so it's going to be positive 1/2. All right, I also know that since this is an upright, smaller image, it is going to be a convex mirror. And that means that it's going to have a negative focal length. I give you the magnitude of the focal length here. And now I want to know what P is. Is that all that I know? Looks like it. I also don't know what Q is. So I have to solve this system of equations. I know that M is equal to negative Q over P. All right, so actually, no, I'm sorry. We don't need to do that. We can, since I know that my magnification is 1/2, I can say that this is equal to negative, pardon me. So let me pause here for just a second. Okay, sorry about that. I had a little hiccup. So I know that my magnification is negative Q over P, which I can do here. And I also know that P, no, I don't know P, but okay, sorry about that. I sort of had to get my head screwed on straight. So here, I know that my magnification is negative Q over P. And I know that my magnification is equal to 1/2. I also know from the lens equation that 1 over F equals 1 over Q plus 1 over P, right? So I don't know Q and I don't know P, but I have this relationship between Q and P right here, so I can substitute in. So I can say then that that negative 2Q equals P. So Q then is equal to negative P over 2, all right? So I'm going to put that in up here. I'm going to come up here, and I have 1 over the focal length, which is 1 over 20, equals 1 over negative P divided by 2 plus 1 divided by P. I'm going to simplify these fractions. I'm going to give myself some more space here. Get rid of this. So 1 over 20 equals negative 2 over P plus 1 over P. And so 1 over 20 equals negative 1 over P. Oh, and excuse me, the focal length here should be negative. All right, so that gives me, because it was, or we decided up here that it is a convex mirror because it has a big object and a small image that is upright. So here I can find that P is equal to 20 centimeters. So on this problem, it required a substitution solving this simple system of equations. Okay, so Ansel places an object 30 centimeters from a thin convex lens along an axis. Real image forms at a distance of 10 centimeters. What is the focal length of the lens? So my P is 30 centimeters. I have a Q equal to positive 10 centimeters. It's positive because it's real image. And I just want to know the focal length. So I have the focal length equals 1 over Q plus 1 over P. The inverse of that, that's 3 over 30 plus 1 over 30, that's 4 over 30, or 30 divided by 4, and that's 7.5, of course. The easiest way to correct for spherical aberrations in a lens is to use an aperture. In an intersection of hallways, a convex mirror is mounted high on a wall to help people avoid collisions. There's a radius of curvature of 4 meters. That means the focal length is 2 meters, but it is a convex mirror, so the focal length is negative 2 meters. What is the magnification of a patient 2 meters away? So again, I need to find Q, 1 over F minus 1 over P. So that's negative 1/2. So Q is equal to negative 2 meters. Or excuse me, negative 1 meters. And then if I want to find my magnification, it's negative Q over P. That's equal to negative 1 over 2. That's positive 1/2, which jives with what I know about convex mirrors, because convex mirrors produce upright, smaller images. And so C is the right answer. Human eye has a lens that can change its focal length. What is focal length of the eye's lens? The largest. It's the largest when the object is far away. All right, because when the object is far away, the rays are parallel and they focus at the back of the retina. That's the largest that your lens will ever get when your object is very, very far away. Concave lenses and convex mirrors are what class of optical devices? All right, concave lenses look like this. Convex mirrors look like this. They look like security mirrors. These are both diverging devices. What type of lens is this? Well, it's convex on this side and planar on this side, so it's plano-convex. Mirages are a result of refraction. Because of the atmospheric refraction, the sun appears at sunset even though it is below the horizon. For a single lens system, virtual images are always on the same side as the object. That would be like a convex lens, for example, where I have my object inside the focal point and my image is outside the focal point, like a magnifying glass. The same is true, by the way, for concave lenses, so the image is smaller. A convex lens is a magnifying glass. What type of image is formed when you use this type of lens as a magnifying glass? Well, as I just said before, it's a virtual image. You stand 1 meter in front of a flat mirror. What is this between me and my image? All right, well, here's me. This is 1 meter. My image is also 1 meter. And so I stand 2 meters from my image. A flat mirror may form a virtual mirror only behind the mirror. That's the end.